In this video, we will discuss the basic theory of chemical kinetics. What we have been writing as R sub A so far is a function of concentration of all the species, temperature, and a few other factors. We will first discuss the contributions of concentration and temperature on the rate of formation or disappearance of species A. Now, if we are interested in finding out how fast this reaction is going to give the product, we have to first understand what happens at the molecular level. Let us take this as molecule A, and let us take a slightly bigger ball as molecule B. Now, in order for this molecule A and B, let us take this product to be a simple C. To form compound C, first they have to interact. In order to interact, they have to collide. It is not sufficient that they collide, but they have to collide at the correct angle also. Giving the example, let us take molecule A as the hydrogen molecule, molecule B as the chlorine molecule, and our intention is to produce hydrogen chloride. Now, when hydrogen and chloride collide, we anticipate that they collide with the correct angle. If they collide head-on, probably we will have bond rupture and bond making, but then we will have free radical formation. This is possible. But it would be better if hydrogen and chloride molecule would collide sideways to produce two hydrogen chlorides all at once. Now, what happened in this sideways collision is that upon the collision, with proper orientation and proper energy, that we were able to rupture those two bonds, and we were able to make two new bonds. So we now know that our molecules should collide with proper energy and with proper orientation. The energy of this collision, the concept of energy of this collision is embedded in two factors. One of them is the activation energy of the reaction. Remember that we have been writing this is the activation energy, and the orientation. The orientation factor is hidden in the first term of K0. And at the end of the video, we will understand, we will relate those two factors to the global thermochemical information. In other words, that this reaction is going to have an enthalpy change, a Gibbs free energy change, and of course, those two are related through a factor of entropy change as well. So we are going to relate those terms to the kinetic parameters, the rate constant, K0, activation energy. So the energy of this collision is related to the activation energy, but also to the enthalpy changes. So the energy of this reaction is related to the activation energy, enthalpy change, and free energy change, while the orientation of this collision is related to the pre-exponential factor. Now we are going to discuss the concept of an elementary reaction. Well, if a reaction is comprised of a single bond-making or bond-breaking step, it is most probably be represented through elementary kinetics. In other words, we can express the rate of formation of the AB molecule to the frequency of the collision of A molecule with the B molecule. The frequency of the collision of the A molecule and B molecule is going to be proportional to the concentration of A and concentration of B. If we can write the frequency of the collision through their concentrations raised to the power of their stoichiometric coefficients, then we call this reaction as elementary. Not all the reactions are elementary. The reactions may undergo complex schemes before they can form the product, and during that those complex schemes, the reaction may take several steps to form the product, and we have to account for those elementary intermediate steps. As a result, our final kinetics could be different from what is represented by the concentration of the species raised to the power stoichiometric coefficients. But let's first discuss an elementary reaction. Let's take this elementary reaction, even a simpler elementary reaction of A going to products, such as an isomerization reaction or a cracking reaction. This molecule A is going to overcome an activation barrier through the reaction coordinate. This is the reaction coordinate. And this is the energy. The reaction coordinate versus energy diagram starts with the reactants. This is our reactant A. Let's say that our product is here. Product has less energy than A. As a result, it has to give away the difference. But A doesn't go to products immediately. It has to overcome an activation barrier. Okay. This activation barrier is the energy required to form a transition state that we indicate by a double dagger. This point is the transition state. Where we presume that an activated complex forms, and this activated complex goes to the products without any barriers. Right? So this is the enthalpy change of the reaction. So this barrier going from A to the transition state is the barrier for the forward reaction. We also have another barrier if we take the product going back to the reactant. Okay? So this is going to be the barrier of the reverse reaction. And from this graph, you can figure out that the difference between the forward and reverse activation barriers is equal to the enthalpy change of the reaction. So let's write here for clarity. So we have one single barrier between A and the products. The peak point of this barrier is called the transition state. A has to have sufficient energy to go over this barrier before the products are formed. And there's a simple relationship between this A and A in the transition state and this transition state going to products. Now we are going to dissect this process in two steps. One where A is equilibrated with its transition state. The second one is that transition state rolls over to the product. So we have A going to its transition state, and this A at its transition state, I will use single dagger for simplicity, is rolling over to the products. Now let me put a circle here to indicate that A and its transition state are equilibrated. We're going to go back to the concept of equilibrium and discuss this further. However, just let's use this concept of equilibrium to understand what is going on between A and its transition state. When A is equilibrated with its transition state, the net rate of forming that transition state is 0. So in other words, rate forward is going to be equal to rate reverse. Forward rate, let me continue through the top, will be K forward to transition state times CA, and rate reverse will be K reverse to the transition state times CA dagger. However, in this second irreversible step, our rate is K2. Let me call this 1, let me call this 2, rate forward 1, rate reverse 1, K forward 1, K reverse 1. To differentiate, this is rate 2, K2 times CA dagger. Now CA dagger is elusive. It's very difficult to measure. It's equally difficult to calculate. Hence, we have to use our imagination to find a way to relate this concentration at the transition state to measurable quantities, such as concentration of A in the beginning. Now, this relationship gives us an opportunity to get CA dagger in terms of CA and hopefully to the thermodynamic parameters that we can measure. Now, let's take this one and work around it. Let's take this one and work around it. K forward dagger is K forward 0 dagger going 1, 0, K forward 1, 0, the pre-exponential, times the activation barrier, right? E to the EA forward. Times CA. This is going to be equal to K reverse 1 dagger. Now you see when my transition state is rolling over to A, it does without an activation barrier. There's no activation barrier. If this transition state molecule wishes to roll back to A, it doesn't have to overcome any barriers. So this is K. This is K 1 reverse 0 with no activation barrier times Ca dagger. Now I can solve Ca dagger from this equation, substitute in here. Let me do so. Ca dagger is equal to K forward 1, 0 divided by K forward K reverse 1, 0 times EA forward times CA. I will take this one, substitute in here to substitute in here to have an expression for R2. K2. Now this K2 doesn't have any activation barrier also, times Ca dagger. Let's substitute. Misprint to be corrected. Okay. So times e to the minus EA forward over RT times CA. Now we will examine this group of quantities. Okay. Now let me go back here again. And write this in the simple form. I will continue upwards. I will write Ca dagger to be equal to K forward 1 dagger divided by K reverse 1 dagger times Ca. Now our notion of chemistry dictates that we take this as the equilibrium constant of forming the transition state, the activated complex, from the reactant A. So I'm going to rewrite R2 as K2 times K equilibrium dagger times Ca. So with that, I now have the rate of A going to the products represented in terms of a rate constant with some complexities in itself times Ca. If I can do that, this is an elementary reaction. Right? this is elementary kinetics. Now we are going to focus our attention on this K equilibrium star, the transition state, formation of the transition state, and how it is related to the thermodynamic parameters that is related between the transition state and the reactants. Now let's remember the concept of chemical equilibrium and the equilibrium constant. The chemical equilibrium is the result of the driving force between the reactant molecules and the products. The driving force between the reactant molecules and the products drive the reaction forward. Let's say that we have a reaction of A going to B, an isomerization reaction, a unimolecular isomerization reaction. There is a driving force that A wishes to be B, that the bond structure is going to change. This driving force pushes the reaction forward depending upon the thermodynamic state variables such as temperature and pressure and concentration. This reaction may or may not go to completion. In other words, all of A is transformed to B or not, depending upon the value of the state variables. Now, those state variables identify the chemical potential of A and the chemical potential of B, and the difference between those two chemical potentials identify how fast this reaction moves forward. What is chemical potential? So the chemical potential difference drives the reaction forward. What is chemical potential? Chemical potential, in the sense that we will use in chemical kinetics, is the partial derivative of the total Gibbs free energy of the system contents with respect to the number of moles of component I, keeping temperature, pressure, and the component, number of moles of the component, all other components different from I. We give a shorthand notation of mu I to chemical potential, and it is the difference, chemical potential difference between molecule A and molecule B that drives the reaction forward. Now that we have defined the chemical potential and then we have defined the driving force for the chemical kinetics, that we can now understand that as the reaction moves forward, it slows, because the chemical potential difference between the reactant side and the product side becomes less and less and less and less. And when the chemical potential difference between the reactant side and the products diminish, then we call this reaction to be at equilibrium. In other words, at equilibrium, we have mu A to be equal to mu B. At which equilibrium? At chemical equilibrium. Right? Since the chemical potentials are the partial molar Gibbs free energies, the partial derivative of the total Gibbs free energy with respect to component I, the equilibrium constant must be related also to the Gibbs free energy. I'm not going to go into the details of deriving the equilibrium constant from the definitions of the chemical potential, but I will write a familiar relationship that we very frequently use to estimate the equilibrium properties, equilibrium state of a chemical reaction. Now, minus R times T times ln of K equilibrium is the Gibbs free energy change for that reaction. Or equilibrium constant is equal to minus e to the minus delta G over RT. So let's start from this level of understanding of the relationship between the Gibbs free energy and the equilibrium constant and the temperature. And let's go back to our transition state reaction, our reactant going through its transition state, and let's relate its equilibrium constant to the Gibbs free energy of formation of that transition state. So I can write this for any reaction. I can write this for the reaction that takes my reactant to its transition state also. So I have K equilibrium going to the transition state is going to be equal to e to the minus delta G of the transition state over R times T. Now this delta G by definition is equal to delta H minus delta T delta S. And of course, this is true for the delta G of the transition state as well. I will substitute e to the minus delta H dagger over RT times e to the minus minus plus, t's cancel, delta S dagger over R. What was K equilibrium? This was K forward divided by K reverse. What was that? This was K0 times e to the power e forward over RT. Remember, the reverse rolling back to the reactant side was non-activated. Now let's relate this side of the equation to that side of the equation. We are going to compare and equate similar terms. On this side, we have a minus activation energy divided by RT term. On that side, we have minus delta H dagger divided by RT term. So we have on this side the K0 going to the transition state term. We have the entropy term. So you see, somehow, if you go back to the initial discussion that when we began, we said that the molecules have to collide with proper orientation. Now we have a term that reflects the orientation of the collisions. It is the K0 term, which is related to the entropy change of the transition state formation. So somehow the orientation orientation of the collision. That information is hidden in this term. The activation energy term is related to the enthalpy change of the transition state formation. So let us go back and look at the enthalpy change of the transition state formation. It is enthalpy of this state, the difference between the enthalpy of this state and the enthalpy of this state. So this is delta H of the transition state, right? For the forward side, which is equal to the activation energy of the forward reaction. So, summarize, K0 is equal to e to the delta S dagger and activation energy is this. So now we have tools to relate the chemistry to the thermochemical information. As I mentioned, it's not trivial to measure the transition state, the activated complex. It's not trivial to calculate, but tools are available. In this video, we are going to continue relating theory of chemical kinetics to thermodynamics. So we have already established that going from A to B, the isomerization reaction the reaction occurs due to a difference between the chemical potentials of the species A and B. The driving force for this reaction is the chemical potential difference. The chemical potential is defined as the partial derivative of the total Gibbs free energy with respect to the number of moles of component I, keeping temperature, pressure, and number of moles of component J that are different from I constant. And from this point, we have already jumped to the level that we related the equilibrium constant to the Gibbs free energy change of the reaction. And then we wrote equilibrium constant in terms of the Gibbs free energy change of the reaction, universal gas constant, and temperature. Then we related the equilibrium constant to the forward and reverse rate constants, and the Gibbs free energy to the enthalpy and entropy change of the reaction. So let's draw the energy versus reaction coordinate diagram one more time. We have transition state here, reactant here, product here. In this case, we have B, and the difference between the transition state and the reactant is the activation energy of the forward step, while the difference between the transition state and the product B is the activation energy of the reverse step. So now we are going to write the rate constants of the forward and reverse steps. The forward step has a pre-exponential and the activation energy. The reverse step has a pre-exponential and the activation energy. And they are related to, let's separate this side of the equation. They're related to the enthalpy change and the entropy change. Now let's group these parameters. I will call this ratio K0 forward divided by K0 reverse as K equilibrium 0. Then I will do a small algebra here. We're going to have e to the raise to the power minus e forward minus in parentheses e reverse divided by r times t. And this term is K equilibrium 0. When we compare this side of the equation with that side of the equation, we see an analogy. We have a term which is independent of temperature. This is K equilibrium 0. We have another term which is independent of temperature, that is the entropy change due to the reaction. We have a temperature-dependent term with almost identical functionality. On this side we have E forward minus E reverse. On that side we have delta H reaction. Now E forward minus E reverse, let's take those two terms. And let's see. On this side we have E forward minus E reverse. We left minus and RT behind. On that side we have delta H reaction. Now let's examine if this is true. This is E forward. This is E reverse. And the difference is indeed the delta H reaction. So this is how the driving force and rates are related. Now we have said that when the reaction is just beginning, it is far, far, far away from equilibrium, and there's a big chemical potential difference. As the reaction moves forward, it approaches to the thermodynamic equilibrium, and the difference between the chemical potentials diminish to the extent that at equilibrium there is no chemical potential difference. At equilibrium, the chemical potential of the reactants and the chemical potential of the products should be the same. There's no driving force. Let us relate this to the rates. Now, I'm going to draw a diagram where my product A is going to go to product B. With a rate of K times CA. This is my forward rate. It's going like that. The reverse rate, which is also elementary, should be, this is K forward, K reverse times CB. Now, initially, there is no B. Everything, the whole system is composed of molecules A. As the reaction proceeds, some B starts to form, and as a B starts to form, reverse reaction starts to take place. Initially, by a minute amount, but as the reaction proceeds, this is going to increase, 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 and eventually will be equal to the forward rate. The point that forward rate and reverse rates are equal are called the point of chemical equilibrium. We have rate reverse and rate forward being equal. On the other hand, as the reaction proceeds, I'm going to use double arrows to demonstrate the net rate. Our net rate is going to get smaller and smaller. Our net rate is going to get smaller and smaller. Eventually, it will be 0. Okay? So this is the net rate. The thick, dark arrows are our net rate. Our net rate in the beginning of the reaction is fast, but as we move closer to equilibrium, it becomes very slow, and at the point of equilibrium, the net rate is equal to 0. So let's write, at the point of equilibrium, at the point of chemical equilibrium, net rate, which is the difference between the forward rate and the reverse rate, is 0. So we are going to use this concept to prove our point here. We are going to derive similar expressions from our conceptual understanding of the rates and relate kinetics to thermodynamics. So rate forward was K forward times CA. Rate reverse was K reverse times CB. And at equilibrium, it's 0. So let's rearrange. K forward times CA should be equal to K reverse times CB. Let's bring similar terms together. K forward over K reverse, which is equal to CB over CA. Remember that we have the same term here and here. And this is the equilibrium constant. Now we have related the equilibrium constant to the concentrations. for this elementary unimolecular A goes to B type of a reaction. Now, how this is going to help us? If we know the rate of the forward reaction, and the rate of the forward reaction not only in terms of the rate constants, but also in terms of activation energies and the concentration functional dependencies, in other words, the reaction orders. And if we know the thermochemical information, the enthalpy change and entropy change and Gibbs free energy change of the reaction, and that information is available in thermochemical tables, we can estimate the reverse rate constant and the reaction order. So we can arrive at a generalizing conclusion from here that the equilibrium constant is equal to concentration multiplication of the concentrations of the species I raised to the power of their stoichiometric coefficient. So let's use this general expression to derive this. This is Cb raised to the power nu b times Ca raised to the power nu a. Nu b is +1, products are positive, reactants are negative, so we have Cb over Ca. Okay, so this is the most general form of the equilibrium constant in terms of the concentrations. And now if we know the equilibrium constant, and if we know the forward rate, then we can obtain the reverse rate, because everything is tied together.